Hey there, and welcome to this next video on foundation level mathematics. So we're moving on to a new topic today, which is geometry, a study of shapes and lengths and angles and space, things like that. Um, and we're going to start with two-dimensional shapes. So here's our plan for today. So there's a lot to cover, lots of little things really to cover for two-dimensional shapes. So we're going to look at the very foundation first, just distances and angles. How do we deal with them? What their properties are. We're going to look at our most basic of shapes, triangles and quadrilaterals, which are just our three and four sided shapes. Then we're going to extend that in general to polygons, which is uh, shapes with straight sides, but of any number of sides, essentially. And then we're going to look at circles, simplest of curved shapes that we can deal with. And then finally, perimeter and area. We'll look at what those are and how do we calculate those for our different types of shape that we've gone over. So first of all, distances and angles. So distance, very straightforward. Just how far we go from one point to another. In various contexts, we might have, say, length, width, and perhaps even depth as we move on to three-dimensional shapes. So, distances can be referred to by these different words depending on the context. So distances can be curved, but the shortest distance between 2 points like this, so if we have a curved distance like that, there's any number of curved distances you could have, but the shortest one is always going to be the straight line between those 2 points. And we have various units to measure length. So we've looked at units before. We have metric system and imperial units. So metric would be things like meters, kilometers. Imperial would be things like, say, miles or feet and inches, things like that. But typically, you're going to be working with meters, centimeters, kilometers, the metric system. So, okay, that's distances. Let's look at angles, which are a bit more complicated. So, what is an angle fundamentally? It's essentially a measure of rotation. So, in the simplest case, say if we've got a rotation from one line to another, so you could imagine like there being a pivot point, and we're thinking, okay, how much would we have to rotate one line to then go and match the other line? That would then be our angle, and we have the full rotation. A full rotation of like a complete circle, we represent as 360 degrees. And this number is just a number that has been chosen because it's highly divisible. Like we can divide that up into many, portions without necessarily going to a decimal number, which is handy. It's kind of like the same reason why we have, 60 minutes in an hour or 60 seconds in a minute, because these are just highly divisible numbers. So we could measure this, using a protractor like this, and you can see this one's going to be 40 degrees. So you see, we line up the zero with the bottom line, and then we can read round to the top line and see that's going to be 40 degrees. So you kind of got two lines there, whether you're reading the angle that way or reading it the other way, like clockwise, counterclockwise. So we get 40 degrees. What does that mean? Um, so 40 degrees, like we've seen, like 1 degree is basically one out of a full rotation of 360 degrees. So 40 degrees, it's like we have 40 degrees out of a total of 360 degrees. This little rotation we have here is essentially like 1/9 of a full rotation. And this is an important property to be aware of that you would need to use in certain circumstances. It's kind of like the same thing we've seen before with proportions, percentages specifically. Like say if you have 20% and you want to put that as a fraction, well, you remember that percent is per 100, so it's 20 out of 100. There you go. You have a fraction that you can then simplify, or do whatever with. It's the same thing here. 40 degrees, a degree is basically out of a total of 360. So 40 degrees is 40 out of a total of 360. Great. There you go. You have your fraction, and then you can just simplify, and we get, 1/9. So yeah, be aware of that property. If you want to turn, like, say, degrees into a proportion, like a fraction, that's how we would do that. So then see what fraction of the full rotation we have. We'll see angles can also be used for other types of rotations. So say if we have a little shape like this, and you imagine rotating it around its own center, like that, like say a 45-degree rotation. Or you could imagine having some point like this, and imagine there being like an invisible line joining the shape and the point, and then you're rotating it around that point. say 90 degrees in this case. And so all those different types of rotation you could imagine, we can use degrees to measure that rotation essentially. So that's what degrees are. And we have different sort of categories of degrees that you might have seen scattered around the presentation here for different angles based on their size. So first of all, we've got, say, right angle, straight angle, and full rotation, which represent very specific amounts, 90, 100, and 360 degrees, respectively. And then finally, we've got more like a range of degrees, like, say, acute angle, obtuse angle, reflex angle, which is 0 to 90 for acute, 90 to, between 90 and 180 for obtuse, and then greater than 180 is reflex. So yeah, you want to be aware of these key words because they might be used in some question where they say, oh, this angle is going to be obtuse, and you need to know what that means. It means it's going to be greater than 90 but less than 180. Acute, obtuse are the ones you'll probably come across more often. Reflex you might come across, but it's less common. So let's move on to triangles and quadrilaterals. So first of all, triangles. So triangle is just any shape made of 3 straight sides. So we're not doing much calculations here. We're looking at a lot of just definitions, keywords, and properties of shapes that you want to be aware of. So here we have 3 different types of triangles based on their properties. The equilateral triangle is the first one, which is one like this. And you have 3 equal angles and 3 equal sides. And we can work out what that angle would be because all the angles inside a triangle add up to 180. We'll see a bit later why exactly that is, but I'm sure that might be something you're already aware of. And if we divide that by 3, because there are 3 equal angles, each one's going to be 60. Next one we have is what's known as isosceles. So this is a triangle that you will come across quite a lot. So it looks something like this, where you've got 2 equal angles down there in the bottom and one other angle at the top. And you see these 2 sides here that I've put a little red line through. This is what we typically use to denote sides, well, to indicate sides that are equal to one another. We use, a little line through it like that. So those 2 lines are equal. We've got those 2 equal angles as well. So if we're given one angle, we can always work out what the other 2 would be. Like, say, those bottom 2, because we know they're equal, and because all the angles add up to 180, if we subtract the 40, that leaves 140 degrees left over, which is evenly split amongst those bottom 2. So divide that by 2, we get 70. Or vice versa. Like, say if we was given that bottom angle of 70, we could do a calculation like this because we know, okay, we're going to get 2 of those angles. So 2 lots of 70 and subtract that from the 180, it will leave us with 40, which is the one remaining angle. So yeah, given one angle, we can work out the other 2 in an isosceles triangle. All other triangles are what are known as scalene. So that'd be something like this. We've got 3 different angles, 3 different sides, and you would just need some other information in order to work out any of those angles or sides. So that is something we'll kind of encounter a bit more, or perhaps a little bit in trigonometry when we study triangles in more depth. So quadrilaterals now. So quadrilateral, quad meaning 4, is a 4-sided shape made up of 4 straight sides. There's 5 main types of quadrilaterals we need to know. So you've got some of the basic ones like a square or a rectangle where there are 4 right angles, making up the shape. And the square, all sides are equal, all angles are equal. In the rectangle, it's just opposite sides are equal to one another, and that's a very important property you need to know when you've got, say, parallel lengths. You've got, like, say, vertical lengths, and then you've got horizontal lengths and opposite. To be able to compare opposite sides, we're going to see that a bit more later. But yeah, rectangle opposite sides are going to be equal to each other. Then we have rhombus and parallelogram, which are very closely related to squares and rectangles. So you see a square like that, where I take a copy and I'm just going to stretch it a little bit. That essentially forms a rhombus. So a rhombus is, a square that's just been, like, slanted. And you'll see opposite angles will still be equal, but they're not all equal to, 90 degrees anymore. And you have the same thing with a rectangle. If you imagine just kind of slanting it, it produces a parallelogram, which is something you'll probably come across more often than rhombus. But a rhombus is just like the same thing as a parallelogram, except all sides are equal. And yeah, with a parallelogram, not all sides are equal, but you still got the same thing of opposite angles being equal to one another. So over those little visualizations that help you sort of see those relationships. Finally, we have a trapezium, which is like a rectangle, but it's been, rather than slanted to one side, it's like you've slanted both sides inwards. And if you do that, both of them in the same way, you find we still get these pairs of equal angles. But all the sides could be different. Well, except for the ones on the left and right there. Right, so let's move on to polygons now. So polygon, we need to know what the word polygon means. In general, that polygon is just a side, a two-dimensional shape made up of straight sides. So many polygons have unique names, but we only need to be familiar with those up to maybe about 10 sides. So we've got a little list here that you want to make sure you're just familiar. Again, a lot of keywords here. So triangle, square, familiar with. What you want to do is be aware of the prefixes of those words. So you've got pen, hex, hep, oct, non, and then dec. Those prefixes literally mean 5, 6, 7, 8, 9, 10 respectively. And then you see, so then you've got pentagon being a 5-sided polygon, hexagon being a 6-sided, heptagon being 7-sided, and so on. So yeah, it's important to be aware of those prefixes because you'll see them cropping up in different places. Most of the time, we're interested in regular polygons, so this is where all the sides and angles are equal to each other. But sometimes you might get irregular polygons where they're not. So, okay, the regular polygons would look like this for 5, 6, 7, 8, 10, even 12, which would be called a dodecagon. And you might notice something as you increase more and more size, it starts to look more and more circular. So yeah, a little interesting fact, as you go up to like an infinite number of sides, it essentially converges towards an actual circle. Although I'm getting ahead of myself here, we'll be looking at circles later, but it's just a little fun property there that maybe you haven't noticed before. Yeah, as you take more and more sides, it starts to look more and more like a circle. So let's look at interior-exterior angles. So this is a very common type of problems that you'll encounter trying to calculate interior and exterior angles. So what are those angles, first of all? So we to work these out, we deal with we need to be aware of the relationship between the size of these angles and the number of sides of a polygon. So far we've considered interior angles, but we also have exterior angles. So say if I take an example like this, where we've got a heptagon, and these are all our interior angles, understandably because they're on the interior of the shape. But we also have exterior angles, and how those are formed. It's not the full angle on the outside. It's basically if you imagine extending these lines out like this of each side, and this little acute angle that's left over, that's the exterior angle. So that's what we refer to when we say exterior angle. And okay, say from this, like just from this information alone, that we have a regular heptagon, and I wanted to find out what is the size of these interior and exterior angles. We can work this out by observing a couple of properties. So say if we let that exterior angle equal to A for angle, and now you see, I'm going to put like a little car down on the bottom left point of that heptagon. And we imagine that we're taking a journey around the heptagon. So, okay, I move along the first line and I get to that first point and I now need to rotate. How far do I need to rotate? It's that exterior angle A that we've just got over there on the left. Great. So, okay, I've rotated A and I continue along and I get to this point and now I'm rotating that exterior angle again. So I've now rotated that A angle twice. And I go to the next point, and you see I rotate that angle again. And we keep doing this as we're going all the way around the heptagon. And what you'll notice is you'll basically get A plus A plus A 7 times, which is 7A. So, okay, as you go round, you've basically rotated that exterior angle 7 times to go all the way around. Well, because we've gone all the way around the shape, we've basically just done a full 360 degrees, haven't we? And come back to where we started. So that's equal to 360. And so by dividing both sides by 7 here, we've got a little algebraic expression we can find the angle, that exterior angle, to be 51.4. So that's how we can calculate the exterior angle. So say a seven-sided shape, 7 lots of that exterior angle will equal 360 degrees. And this is the same for any shape. You say like a pentagon, um, it'll be 5 lots of that exterior angle will equal 360. And so then you can work out, one would be, it'd be 72 degrees and so on. So we can do this for any shape. And so therefore, say if I let B be the interior angle now, we can deduce that's going to be 128.6 because the interior and exterior angle there, you see they make up a straight angle. So they're equal to 180 degrees together. And so if I do 180 degrees minus the 51.4, I get the interior angle. And this is how we can actually show the well-used property that we have, that all the interior angles of a triangle add up to 180 by doing this technique. So you might want to try that yourself. If you draw like a triangle, um, you'll show that all the interior angles of an equilateral triangle will be 60. But you could try this even for an irregular triangle. And you'll see that you can't find out the interior angles specifically, but you can show that they're going to add up to 180 degrees. So let's look at a more abstract scenario now, that where we might be given a situation where we just have a particular point of a polygon and we're given an angle. Like say if we've got something like this, like a particular point of a polygon, and we've got the interior angle of 156 degrees, and we want to use that to determine how many sides this polygon has. Well, using that property that we just saw a moment ago, the relationship between exterior angles and the number of sides, we can do that same thing, but in reverse. So, okay, first of all, what is the exterior angle? It's going to be 24, because I just do 180 minus 156. And now, well, I know however many sides there are to this shape, it'll be that number times by 24 will equal to 360. Which, okay, if I wanted to put that as a little equation, let n be the number of sides, the unknown number of sides. Well, that n times 24 is going to get 360. And so you basically get this little expression, little equation, sorry, for n. And, well, if I just divide both sides by 24, you get 15. And so, okay, whether you want to form an equation or just, work it out more logically, you see we can find the number of sides must be 15. So that's how we would work that out. So you see that relationship between the number of sides and the exterior angle. You need to know how to apply that in both directions. So given the number of sides, you can determine interior and exterior angles. Or given an interior or exterior angle, you can work your way back to the number of sides. This is a very common thing throughout GCSE math, in fact, where you might be given a property and you make sure you're comfortable doing it in both directions. So that way, yeah, you'll be able to get these marks in your exam no matter what. So let's move on to circles now. So we looked at polygons, all straight-sided shapes. Circle is the first shape we look at really with a curved side. It's the most simplest curved shape you can get, where you've just got a single point, and in we're drawing basically all the points that are some constant distance away from that. So circle, yeah, it's not a polygon because polygons are made up of straight sides. This is just one continuous curved side. Circle is basically all the points that are some constant distance away from another point. It's kind of an example of what's known as a loci. Won't get into that right now, but you'll see what exactly I mean by that when we look at these keywords relating to a circle. So a radius. A radius is this, basically the distance from the center to some point on the circumference, any point on the circumference. Because you see, as I sort of rotate this round, it's the same distance in all directions. So that's kind of fundamentally what a circle is. Then we have the diameter, which is basically 2 lots of the radius. The diameter being going from one point on the circle to another point on the circle, going through the center. It's basically just 2 radiuses next to each other, or radii is the plural for radius. So that's diameter. Chord. Chord is kind of more general form of the diameter. So diameter is going from one point on a circle to another through the center. A chord is going from one point to another, any 2 points, not necessarily going through the center. So that's an example of a chord. You probably won't come across chords so much though at foundation level, but it's good to be aware of what that term is, in case you do. And then finally, circumference is the distance all the way around the outside, that curved distance. Um, Now, what I can do is draw, say, two lines like this, go into each end of that chord. And if I fade everything else away, what we have here is what's known as a sector. So given a particular chord, you can essentially define a sector like this by, drawing two radius lines to each end of the chord. And you can imagine just like a slice of pizza or a slice of cake. That's essentially what it is. And a sector and a chord, yeah, you see that there's this relationship between those two. And then we have this curved length here. We'll look at how we measure this distance here. It's what's known as an arc. So it's basically like part of the circumference, just this little slice. Um, and then finally we can get what's called a segment. So you see between the chord and those two radius lines, we essentially formed a triangle. If we could find that triangle and take it away, what you're left here is what's known as a segment. Kind of like a segment of an orange or something. You see, it's got that kind of shape, um, so that's what we call a segment. Again, a lot more sort of key words here that you just need to be aware of, so that when you have a question talking about sectors, segments, or whatever, you know what that means. So let's move on to actually doing some real calculations now. We've done a lot of definitions, a lot of properties of different shapes, and now we're going to kind of bring it all together. So perimeter. A perimeter of a shape is the distance just going around the outside. So imagine earlier that example we had a heptagon and that car going all the way around the outside. You can imagine being like, okay, how far has it traveled going all the way around? That's what perimeter is. We can calculate perimeter of a shape by calculating the length of all the sides uh, where needed and adding them all together. So typically you'll get something like this, like more of an irregular shape, and you'd have to kind of break it down into different pieces that we can work with. So say here, we've got a whole bunch of distances, but you see we're missing that distance on that vertical distance in the bottom left and the horizontal distance at the top. How would we work out what those are? Well, we do that by comparing opposite sides. Like you see here, we've got vertical distances and we've got horizontal distances. So if we look at the vertical distances first, you see we've got that 11 and then we've got that 17. If we find the difference between the two, that's going to be this little remaining vertical distance in the bottom left. So 17 minus 11 gets 6. And we can do the same thing with that distance at the top. We look at the horizontal distances. We've got 15 and we've got 6. We can then infer that this one at the top is going to be 9 because it's 15 minus 6. Now we've got all the distances. Well, we just got to add them all up. We've got the distances of every side going around the shape. If we add them all up, that will get us the total perimeter of 64 centimeters. So that's how you deal with that kind of problem there. And you see this as a common theme moving forward, where we can have more complex, irregular shapes. And what we want to do is want to break it down into simpler shapes that we do understand, and then work out each one individually and then bring it all together. That's kind of a typical theme that you'll see with these kinds of problems. So, we've got a special word for the perimeter of a circle. We've already seen this, called the circumference, which is this distance all the way around the circle, like that. And this is what's known, it can be calculated via 2 pi r, where r is the radius. So you see that distance from the center to the circumference is denoted r for radius. And this formula uses the irrational number pi. So this is not something you can really calculate. On paper, you'd have to use a calculator, which can, calculate this value. So pi, it's an irrational number. So it's got this infinite decimal expansion. We can never write it exactly, but we can estimate. And so if we wanted to, calculate this, like I said, we have to use our calculator. So I'll show you an example here with, a standard Casio calculator. You find where pi is. Typically, it's down here at the bottom. So you see this button where it says times x to the times 10 to the power x. That's basically, for standard form. But you see above it, there's that little yellow symbol, which is pi. Okay, how do we actually get that? what we have to do is we have to press this button up here first, shift. And you press that button, and then you press that button at the bottom, and instead of doing times 10 to the x, it'll instead give you pi. So that's how we get down your calculator. You want to make sure you're comfortable in using your calculators for pi, for trigonometry, for powers like squares and square roots and things like that. You might be able to see some of them on the calculator. Most calculators work the same way. If yours is a bit different, that's fine. Just make sure that you know how to use your calculator appropriately, so that you won't have trouble with these kinds of problems. So that's how we calculate the circumference of the circle. Just a little thing to note, because we can put the circumference as 2 pi r. So let me denote the circumference as c for circumference. We could also, let the circumference equal to pi d, where d is the diameter. Because remember, the diameter is 2 lots of the radius. So 2 pi r is the same thing as pi times d. And going back to our lesson we had on proportionality, what this means is that circumference is proportional to diameter. This is how pi was initially discovered. Like, you found circles, as you make them bigger or smaller, the circumference and the diameter always stay proportional to one another, and that constant of proportionality is pi. So yeah, if you look back at some of the stuff we've done on proportionality, you might need to refresh your memory of that. But it is a little property here that you may not have been familiar with. So okay, perimeter. Let's use this to now calculate an arc. So I mentioned earlier we could calculate an arc. And what we need the radius, and we need this angle, and we want to then calculate this arc, this curved distance here. So how we do that is we first of all recognize that this sector is part of a bigger circle. So you see there I've kind of faintly drawn in what that circle would be, and it's like we're taking a slice out of that. In order to calculate that arc, what we could do is find the circumference of that full circle, and then essentially times that by the proportion of the circle that we have. So in this case, the circumference is 2 pi r, like we've just seen. So that's for the full circle. And if we substitute in our radius of 5 centimeters, you see we basically get 10 pi centimeters. So I've left it in terms of pi at the moment because I don't want to have to round my number just yet. So that's the full circle. Quite straightforward. That arc, we need to know what proportion of the full circle we have. Well, this is now going back to what we saw at the start with degrees. So that degrees there, 60 degrees, tells us what proportion of the full circle we have. We've got 60 out of a total of 360. That means we've got 1/6 of a full circle here. And so, okay, if we take that circumference and times it by 6, or basically divide by 6, well, 10 pi divided by 6 gets us 5/3 of pi. And then finally, we can put that into our calculator and round to 1 decimal place, and we'll get 5.2 centimeters. So that's how you deal with an arc. Just apply the formula for calculating the full circumference, and then take the proportion of that full circle that we have here using that. That's why that property between degrees and the proportion of the circle that you have is very important to understand. So we're going to move on to area now. Last thing. So we've looked at a lot of distances. Now we're looking at areas. So what I want to do is quickly just go over what actually area is. So you can imagine, like, first of all, like if we imagine building up our dimensions, a 0-dimensional shape is kind of like a point. And then you can imagine taking that point and dragging it along. It produces a 1-dimensional line. And then it's the same thing again. You imagine taking that line and you drag it up another perpendicular distance. You essentially get, the area that sweeps out is then, the area of that shape. And so that's how, what it essentially means, to be 2-dimensional. And so when we're calculating the area, we're basically calculating what is that space inside that 2-dimensional shape. And you can even do this one step further by dragging that shape through a 3rd dimension, and you create a 3-dimensional cube in this case. But we're not going to be doing that yet. We'll look at 3-dimensional shapes later. So say if I look at the simplest one where we've got a shape, a little square, 1 meter by 1 meter, that area is going to be 1 meter squared, which is precisely why we use the term squared. Like rather than say 1 meter to the power two, we say squared. Well, that it comes from this in geometry where it corresponds to the area of this base unit that we have for area, which is just 1 meter by 1 meter. The area is then going to be 1 times 1 meters squared, which is just one. And so, okay, if we have a different shape or a more complex shape like this, and we're trying to calculate the area, what we're basically asking is, okay, how many of those little squares will fit inside that shape? And in this case, if I sort of fill this shape up, you see, you could count all those up and you see basically it's 20 1 meter squared blocks. And so 20 meters squared is the area. And how we'd calculate that out is by, essentially, if we looked at the sides, the length and height of this shape, you get 4 meters times 5 meters gets you 20 meters squared. Meters times meters getting meters squared. So that's fundamentally what area is and how we do it. So it's quite straightforward for a square or a rectangle. We're going to see how we can gradually build this up to more complex shapes, like a triangle for starters. So say if we've got a triangle with these two sides, and this is a right angle triangle, we can calculate the area of the right angle triangle by just noticing that it's simply half of a full rectangle like this. If I draw these lines in, you see we've got a rectangle and we've essentially just cut it in half diagonally. So, okay, we use our understanding of area that if we do 7 meters times 8 meters, that's going to get us the area of that rectangle. And if we divide that rectangle by 2, we will then get the area of this triangle. So that's where the formula that you've heard, base times height divided by 2 for a triangle, that's the reason why that's the case. And this also applies to more well, not necessarily right angle triangles, any triangle. So even with like an irregular one like this, where we lay it so we've essentially got it flat. So we've got one side is essentially the base, and then the height. You see, the height doesn't correspond to one of those two other sides. It's just it has to be the perpendicular distance to that 15 meters. But you see what we can do here. We essentially divide this down that perpendicular distance, and it essentially creates two right angle triangles where we can essentially do the same thing. Each of those two right angle triangles are half of a full rectangle. And these two rectangles together, we can calculate what that's going to be. It's going to be 15 times 8. And if we now divide that by 2, that's going to get us half that area, which will correspond to what this triangle is. So, which is 60 meters squared. So we're essentially doing the same thing here. We can't find the area of each triangle individually, but we can recognize that each of those triangles individually are half their respective rectangles. And so therefore it's going to be half of the overall rectangle. And so, yeah, we do 15 times 8 divided by 2. So base times height divided by 2 is how we calculate the area of a triangle. You just need to make sure that you set it up correctly. So we can work it out with this where we've got the correct information. But say if we had alternate information like this, then we wouldn't be doing 15 times 10 divided by 2. You need specifically the height, like that perpendicular distance, because remember that going back to the very foundation of what area is, it's two perpendicular distances multiplying is what produces an area. Like two, if they're like this, where they're like diagonal respective to one another, that won't work. So just something to be mindful of there. It's important to understand where these kind of formulas come from so you know how to apply them correctly. So you can take something like a parallelogram. How do we calculate the area of that? It's basically that length times by the height again. So we've got that height of 5 meters and one side length of, the perpendicular side length of 12. You times those two together, you get the area of the rectangle. And it might make sense why that would be, because like we saw earlier, a parallelogram is essentially like a slanted rectangle. But we can prove it more thoroughly here by essentially doing the same thing that we've seen, where we divide a shape up into smaller, simpler shapes. So say here, I could chop it down here to produce a triangle, and imagine moving that triangle over here. You see how it forms a perfect rectangle now, 12 by 5. And so therefore, the area is going to be 60 meters squared. So, okay, so that's how it works with parallelograms. Similar thing for rhombus. We're going to look at trapezium because that one could be a little bit more complicated. We need these two side lengths, the top and bottom, like parallel side lengths, and then the perpendicular height. So we do a similar thing with a trapezium, although it's a little bit trickier. We can rearrange the shape to form triangles and rectangles like this. And you imagine I could rearrange it kind of like this. And you can see I can now infer that other width of 5 meters. And you see now I've essentially divided this up into two smaller problems. Calculating the area of a rectangle and calculating the area of a triangle, which we know how to do. So we can work this out now. Bear in mind though that this is not drawn to scale. Like you see that rectangle to the left, it's actually a square because you can see it's 4 by 4. So yeah, just bear in mind that, and same thing in your exams. Everything will, things are not typically drawn to scale, and so you've got to actually use the information you've been given in the diagram, and don't say something's a square just because it looks like a square, for example. So if we wanted to calculate this, you see that square on the left is 4 times 4. The triangle is going to be 5 times 4 divided by 2. And we can piece all that together and we get 26 meters squared. So that's how we could calculate the trapezium. And you see how we didn't even use a formula or anything there. We managed to work it out just logically. But we do have a formula. You can see this one down here in the bottom right I've had here. And you see where A and B are the two horizontal distances, H is the height. We could essentially do the same thing, and you might want to pause here and take a look at this, and you can see why we're going to get B minus A there for the width of that triangle. And then if we essentially do the exact same thing, but more algebraically, and we try and simplify this by collecting together like terms, you essentially get that expression of half A plus B times H. So you don't need to know like how to prove that, but I just wanted to show you that so you can see where that comes from. And the most important thing is the technique that we're using, where we're breaking up a shape into smaller pieces and rearranging it to make it into something we can solve. That's an invaluable technique to have in geometry. So let's look at quadrilateral now. So quadrilateral use the same basic techniques with many different polygons. So here we have another common quadrilateral is the kite, which you might come across on occasion. So this one's can be a little bit trickier. So we need these two diagonal distances, between opposite points. And if we have those, we can calculate the area. It's going to be basically half times of these two areas multiplied. So that's a little formula you want to be aware of. And if we do that, we essentially get this, which is 75 meters squared. The reason why that is if we imagine dividing this up into triangles like this along those two lines, and if we rearrange it like that, you see we essentially get half of that rectangle, 15 times 10 rectangle, and we've essentially got half of that. So that one's a bit harder to visualize, and we're going to talk about this a bit more in the future about spatial reasoning, being able to visualize shapes in your mind. If you're not so good at this, try actually making some of these shapes out of card or something and cut them up and rearranging the pieces, and it'll help give you that ability to visualize what's going on here, because you can physically move something around, and then you've got that experience for then future reference. So that's something that can be very handy. So right, let's look at just a regular polygon. So okay, we've just got a little bit more left to do. I appreciate this lesson's going on quite long. There's just a lot we can cover in two-dimensional shapes. So how do we deal with a regular polygon? If we have the appropriate distances, like say here, if we've got the perpendicular distance, up to the center from one side, and we've got the length of one of those sides, we can quite easily calculate the area from this, because any regular polygon you could draw lines from each of its points up to the center like this, and you essentially form a series of triangles. And triangles we know how to calculate, don't we? So you see we've got one triangle there, which is, a height of 5 and a width of 6. So we do 5 times 6 divided by 2 is the area of that triangle. Then we times that triangle by 6, because you see we've got 6 of them here, they're making up the pentagon. Because it's a 6-sided shape, you're going to end up getting 6 triangles. Likewise, with an octagon, you'll get 8 triangles, and so on. So you see there, we can find the area of one triangle and then times it by 6, and we get the area of the full hexagon, which is 90 meters square. So that's how you deal with a regular uh, polygon. So, to calculate an irregular polygon, yeah, we'll have to divide something up in pieces, thinking things more generally. So, okay, let's look at area of circle now. So again, like with the circumference, you've got this equation of pi r squared, and we need to just know how to use that. The proof of why that is a bit complicated, but I might show that in some bonus material, like a rough proof of why that is if you're interested, but you won't need to know that for your exams or anything. Just need to know how to use it. So area of a circle is just dependent on the radius. So pi times the radius squared. So that's radius times radius. So yeah, you see how we get that radius squared, because any formula for area is always going to involve a distance times another distance. And again, this uses the irrational number pi. So we can kind of use this. So we know how to calculate the area of a circle. We can use this to then calculate the area of a sector in the same way we kind of calculated the area of an arc earlier. So the area of a sector, so we could calculate the area of the full circle and then calculate the proportion of the full circle we have here. So this angle allows us to determine what that proportion is. So first of all, ignore the sector. Let's just look at the full circle is going to be pi times the radius squared. So the radius being 4.1 centimeters there. If we work that out, you essentially get this. So you might need a calculator for these kinds of problems, because it's we haven't got such nice numbers this time. The proportion, again, it works in very much the same way, even though we haven't got such nice numbers, but 117 degrees is basically, okay, 117 out of 360 is the proportion we have here. So that's 13 over 40. Now we can then find the area of the sector. So we take the area of that full circle, times it by our proportion of 13 out of 40, and that will give us the area of the sector. So, okay, that's how you would deal with the area of the sector if you need to. You just find the area of the full circle, use that angle to determine what proportion of the full circle you have, and then times the area of that circle by that proportion. It'll tell you then how much that slice is. So, right, one last problem let's look at. So it's kind of bringing things all together now, which is a more complicated exam style question you might get, which might be something like this. And say if we've got like a park that the local council is going to make, and you see here we've got area that is green, like the grass, and then a little pond, and we've been given these distances, and this is the problem that we need to solve. So the council's creating a park with a circular pond. Suppose seed for 10 meters or 10 square meters or 10 meters squared, same thing. It costs £1.20. How much would it cost grass to sow grass for the whole park? So how we would tackle something like this? So if it costs £1.20 for every 10 square meters, what we need to know first of all is what is the area of grass, and then we could divide that by 10, see how many lots of 10 square meters we have, and then times that by £1.20 to get then the total cost. But first of all, we need to know what is the area of grass here, and you see it's this very complex shape. But what we can do is divide things up like this into more regular shapes that we're familiar with. So say if we're trying to calculate the area, first things first, we could calculate the area of that big tall rectangle on the right, which is going to be 9 times 21. I know that includes the pond, but we're going to ignore that now, pretend the pond's not there. The bottom left rectangle, you see that's going to be 7 times 6. So you see those distances I've inferred there, the 6 and the 5. Essentially comparing opposite distances, again, like we did earlier. Then finally, we've got that little triangular area, which is going to be 5 times 6 divided by 2. And then finally, we included that pond area in that initial rectangle, but we can't, we don't want to actually include it because, well, you're not putting grass over the pond, are you? So what we do is we take away the area of that pond. So that pond being circular and the radius is 6. So we've got pi times by 6 squared. So now we've got one big calculation here for calculating the area of the grass. We can just work all that out. So you gradually go through your calculator, working out all the different values, bring it all together, and we get 132.90 meters squared to 2 decimal places. So there we go. That's our area. And so if we now want to calculate the cost, we times it by, say, 1.2 over 10. So if it costs £1.20 per 10 meters squared, per kind of implies division. So that's basically £1.20 divided by 10. So if we times it by that, that will get us then how much cost it will be for this grass. So if it's £1.20 per 10 meters squared, it's then basically 12 pence per 1 meter squared. And we know we've got 132.90 meters squared here. So 132.9 times 0.12 gets us our final cost of £15.95. So there we go. So a lot of stuff we've learnt there. And then we've got a typical kind of exam style question here where it's asking you to bring all things together, and you need to be comfortable doing that because typically exam questions will be like that because there's only so many questions you can be asked on an exam, and they want to hit all the different topics, don't they? So you'll get questions where it's pulling on lots of different skills all at once. So make sure, yeah, you're comfortable doing that, like you bringing all those skills together. Right, so let's leave it there. I'll just leave you with just a fun fact about shapes. Hexagons. Hexagons are very useful shapes that we see all over the place in nature and manufacturing and things like that because it has some very useful properties. Like, say, if we look at a hexagon like this, and we could stack it up like this, and it gets a very nice. Not only is it not wasting any space, but you've got a nice even spread of pressure out in all directions, really. Which you don't get with other shapes. Like if we consider, say, like a square and a circle, you could stack up a square, and yeah, you don't waste any space. But a lot of the weight, like say, if this was like crates and the weight's acting down, it's like it's all acting in one direction, whereas the hexagon sort of helps spread it out horizontally as well. Um, and the circle is no good because you see when we stack out, we get a lot of wasted space in between. And so yeah, hexagon is one of the simplest shapes where you have this nice balance of properties here. And so that's why you see it quite commonly in things like, I say, a beehive. Because it has, the bees that they don't necessarily know this, but it just naturally kind of converges towards that kind of shape because it works best. But we, humans use this a lot in, say, manufacturing, like, say, something like nanotubes, where we arrange atoms in these hexagonal shapes, and it makes like a material that is very light and very malleable, but also very, very strong at the same time. So, yeah, very useful shape there that has, real life applications of its, beneficial properties. So, there you go. That's our takeaways for today. All the things we've learned today. Next time, we're going to be taking this up a notch, looking at three-dimensional shapes. So I will see you there for that one.